The main focus of this discussion will be on finding the lengths of secant and tangent segments in a circle. So let's take a minute and review again exactly what a tangent segment is. A tangent segment is going to be a line or part of a line that intersects the circle at exactly one spot. So there's a tangent line right there. It intersects my purple circle at only one spot. A couple of theorems that you need to be aware of with respect for their use in proofwriting. The first one says that any line that's tangent to a circle is always perpendicular to the radius drawn to that point of tangency. So here's what that theorem's saying. They're saying if we have this green line right here that's tangent to the circle at point D, and we draw the radius to that point where the tangent line meets the circle, then they will always meet in such a way that the two will be perpendicular to each other. So the radius drawn to the tangent line always going to be perpendicular. The second theorem that you need to know is that any two tangent segments drawn to a circle from the same external point are going to be congruent to each other. So what this is saying is if we start at point B and draw one tangent line segment to point A and a second tangent line segment to point C, these two will always have the same measure. All right, so that's a little bit of background about tangents, a little bit of background about secants. First of all, what is it? Well, whereas the tangent line intersected the circle in at exactly one point, the secant will intersect the circle exactly twice. And it can be line or part of a line. All right, a theorem regarding secant segments that you need to know says that if we draw two secants to a circle from, there's those words again, the same external point, then the product of the length of one secant in its external part is equal to the product of the length of the second secant and its external part. All right, so this sounds a little bit confusing when we put it in writing, when in fact it really truly isn't that bad. I'm going to go ahead and color code my two secants. I'm going to make one green and I'm going to make the other one purple. What this theorem is saying is that if we take the outside part of the green secant, and I'm going to go backwards and make my writing green, so the outside part times the whole, or the length of the whole green secant, that's going to be equal to the product of what we get when we take the part of the purple one that's outside the circle and we multiply it times the whole thing. So in looking at our green secant here, the length of the part of the secant that's outside the circle is defined by A. The length of the whole secant is B. And if I go look at my purple secant, the part of it that is outside the circle is the part that measures C units long. And the length of the whole thing then is going to be D units long. So in other words, the outside times the whole thing for the green one is equal to the outside times the whole thing for the purple one. You might have guessed it, but in case you didn't, that's going to be a good formula to memorize. Like it, love it, hate it, you do have to know it by heart. The outside times the whole thing is equal to the outside times the whole thing. And that formula is going to come in handy when we go on and take a look at that problem down at the bottom part of the page. This one says if we have a secant segment and a tangent segment that are again drawn from the same external point, then the product of the length of the secant segment and its external part is going to be equal to the square of the length of the tangent segment. I'm going to use exactly the same formula here that I did up above. And like I did up above, I'm going to go ahead and I'm going to color code these. I'm going to make one blue and the other one green. And I'm going to think to myself, let's use that same exact formula here. Let's take the outside times the whole thing for the blue fella and make that equal to the outside times the whole thing for the green one. Now, in looking at that blue tangent, the piece that is outside the circle is the part that measures A units long. The piece that represents the length of the whole segment is also A units long. So the outside piece, the whole piece, are both represented by A. And that's going to be equal to the outside piece for the green one times the length of the whole green one, C. So in other words, if we simplify this or clean this up a little bit, A times A is A squared is equal to B times C. But again, if you just remember the same formula that worked for the example up above, and that's why it's so key that you know that and you memorize that, it's going to work for this one as well. All right, so let's go take a look at some practice problems and how this works. So the first one, they give us these tangents, and they're asking us to find x. So what we've got here is we've got two tangent segments that are both drawn to the circle from the same external point. And you need to remember that theorem on the previous page that says anytime you have two tangents drawn to a circle from the same external point, they're always going to be congruent to each other. So the one on top, which measures x squared minus 4x, is going to be equal in length to the one on the bottom. I'm going to set them equal, and now I've got a quadratic equation to solve. So I'm going to solve this by factoring. I'm going to subtract 21 from both sides. I need two numbers that multiply to be negative 21 and add to be negative 4. So I'm liking minus 7 and positive 3. A negative 7 times a positive 3 is a negative 21. Negative 7 plus a positive 3 is a negative 4. So we find that the two possible values for x are either 7 or negative 3. And if I plug in 7 in place of the x, I get 49 minus 28, which is 21. That checks out with this guy. If I plug in negative 3 for x, negative 3 times negative 3 is 9. Subtract a 4 times negative 3, that's going to be an add 12. That is also 21. Since both of these check, we aren't going to reject either solution, but rather keep them both. That's kind of neat. I like that we get to keep them both for that one. All right, moving ahead to number 2. This one also they want to solve for x. This question, when most kids look at it and see it, they kind of give it a blank stare until they see how it's done. And once they see how it's done the first time, it's like, oh, that's really not a very difficult problem. I'm going to think about these two tangent segments going to the same external point. Because they do, I know they have to be equal in measure to each other. So because the first red tangent measures 4, the second red tangent must also measure 4. Likewise, I've got these two blue tangents coming from the same external point. Because one of the blue tangents has a measure of 3, the other of the blue tangents must also have a measure of 3. And then in a similar fashion, if one of my purple tangents measures 2, the other of my purple tangents must also measure 2. And therefore, the length of segment x is going to be the 2 of the purple segment plus the 3 of the blue segment, or a grand total of 5. So again, now that you've seen it, hopefully you understand how that works and you see that it really isn't truly a very difficult problem. All right, number 3. This is going to be a fun one. We've got two secants. I know they're secants because they both intersect the circle in exactly 2 places. I'm going to make one blue, the other one green. And anytime I have this situation, I'm going to think outside times the whole is equal to outside times the whole. And that's a good formula to write down a few times until you have it memorized. So for the blue guy, the piece of the part that's outside the circle is the 5. The length of the whole thing, be careful, is this 5 in addition to the x that's inside the circle. So in other words, the whole thing would measure x plus 5. And for the green one, the part that's outside the circle is 6 units long. And the whole thing is going to be the 6 that's outside the circle in addition to the 4 that's inside the circle for a grand total of 10. So 5x plus 25 when I distribute is going to be equal to 60, making 5x's equal to 35 and each x equal to 7. Notice how for this problem, because I knew I was going to have to use the length of the whole segment, I labeled the length of the whole segment in the picture. And that might be a really good strategy for you to use as you're working through these also. If they don't give you the length of the whole segment, take a minute and just write it down in your diagram, because that way you'll have it when you need it. Number 4 is a tangent and a secant. Again, I'm going to color code so that I can talk about these guys. I'm going to make the secant green. I'm going to make the tangent purple. But as soon as I see this, I think to myself, outside times the whole is equal to outside times the whole. So I'm going to go ahead and I'm going to start with that purple one. The length of the purple segment that's outside the circle is 6. The length of the whole purple segment, also 6. The length of the green segment that's outside the circle is x. The length of the whole thing, and again I'm going to label this in my diagram, is either going to be 5 plus x, or if you prefer, x plus 5. So again, my very first thing that I'm going to do is distribute through the parentheses. I'm going to subtract 36 from both sides because I've got a quadratic equation. And at this point, I'm looking for factors of negative 36 that add up to 5. And I'm going to hold for a minute and see if you can find those on your own so that you can get some practice in factoring. So hopefully you ended up with x plus 9 for one factor and x minus 4 for the second, making your possible values for x negative 9 and positive 4. If I come over here and look at the picture, x represents my part of my green secant that's outside the circle. I can't have a segment that measures negative 9 units. So for this particular example, negative 9 is an inappropriate solution, and I'm going to reject it, making the length of my green segment equal to 4. Our next example is kind of an interesting one in that they give us a little bit of extra information here. They confuse the picture just a little bit. And I'm going to start out by talking first about what y is, and I'm going to say if that blue tangent measures 12, this blue tangent also has to measure 12. But that's really not what we're looking for in this question, because the directions here ask us to solve for x. So I'm going to go ahead and I'm going to look at that secant that I'm going to make green. I'm also going to look at my blue tangent, and I'm again going to remember that formula, outside times the whole is equal to outside times the whole. So for my blue fella, the piece that's outside the circle is 12. The length of the whole segment is also 12. For the green one, the piece that's outside the circle is x. The length of the whole thing is going to be the 32 inside the circle plus the x outside the circle, or in other words, x plus 32. So once again, after I apply a little bit of distributive property, we realize here that we've got yet another quadratic equation. This is going to be great practice for you for next year when you go on to Algebra 2. And again, we want to factor this. But this time we're looking for factors of negative 144, whose sum is a positive 32. And again, I'm going to give you 30 seconds or so to go find those. So if you found one of the binomial factors to be x plus 36 and the other one to be x minus 4, you were spot on. Together they have a product that's equal to negative 144 and a sum that's equal to 32. So possible values for x here are negative 36 or 4. Again, x represents the length of a line segment. We can't have a line segment with a negative length, making that negative solution inappropriate, and therefore we must reject it. And the value of our x here is 4. All right, I think we're going to go ahead and do one more and then call it a day. So last one for this video, they ask us to solve for x. But what's interesting about this problem is that there's not only an x for a variable in this problem, there's also a y. I'm going to go ahead and I'm going to start with those two chords that are inside the circle, one of which I just made green, the other of which I made purple. And if you think back to the video from last night, and remember what you learned in that video, the product of the two pieces of the purple chord has to be equal to the product of the two pieces of the green chord. So I'm going to go ahead and multiply the two pieces of the purple chord together, 4 times y. That has to be equal to the product of the two pieces of the green chord, or 8 times 5. So 4y is equal to 40, making each y equal to 10. So I'm going to label that in my picture. And some of you might be saying, well, good for you, Mrs. McCann, but who really cares? We didn't want to find y. They asked us to find x. To which I would have to say, I absolutely agree, but in order to find the value of x, you're going to need to know what y is, because I'm going to use that purple secant, and now that I figured out what y is, I know the length of that purple secant and that green tangent. And I'm going to apply to this part of the problem the new rule from today, which says if you multiply the length outside the circle times the whole thing, that's going to be equal to the product of the outside part and the whole thing for the second segment. So for the green tangent, the part outside the circle is x. The whole thing is also x. For the purple guy, the part that's outside the circle is 5. The length of the whole thing now is going to be the 4 plus the 10 plus the 5, or 19. So x squared here is equal to the product of 5 and 19, which is 95. Remember, when you take square roots, there's a positive square root and also a negative square root. The negative square root would be an inappropriate solution here because, once again, you cannot have a negative length. So the value of our x is equal to the square root of 95. Notice that it does not say to round, it doesn't say to find to the nearest integer or to the nearest tenth or to the nearest hundredth, so I'm simply going to leave that in simplest radical form, exactly as it is. There's one more question here dealing with me and my swimming pool. If you want to take a stab at that one, feel free to take a stab at it. If not, we will look at it the next time that you come back to class. If you have questions or there are parts of any of these problems that you don't understand, please make a note of it in your notes right now so that, again, you'll remember to ask the next time that you come back to class.